Okay, Electrochem practice problems, this time with sound. Balance the following equation in acid and calculate E naught. Well, E naught is actually pretty easy to calculate. It's still the reduction potential plus the oxidation potential. It has no value of stoichiometry. The stoichiometry comes in when you multiply by the number of moles of electrons when you're using those problems for those equations for delta G. And E versus E naught and the Nernst equation. However, for this one, it's just a practice on how to balance by redox. So we use our Leos as GER, and when we oxidize, we lose electrons. When we reduce, we gain electrons. So for the reduction, permanganate becomes manganese 2. So manganese goes from positive 7 down to positive 2, so that's 5 electrons transferred. And the iron is my oxidation. It goes from iron to iron 2. So I add 2 electrons to my product side. Lose electrons during oxidation. Gain electrons during reduction. All right, so that takes care of my atoms and my electrons. AEI, add in the ions. And it's in acid, so we're going to use the H plus ion. And we had a -6 charge on the manganese side for reactants, so I added 8 H pluses to make the charge positive 2 on both sides. For the iron half reaction, the oxidation, they were both 0 total charge on both sides, so I didn't have to add in any ions. Oxygen, balance the oxygens. There's 4 oxygens in permanganate, so I added 4 water molecules. Now, unify the 2 equations, so I multiply the top equation by 2 and the bottom by 5 in order to get 10 electrons in both half reactions, so they cancel out. And then I add the 2 together, and there's my balanced equation. As far as the voltage goes, I just have to look up the reduction potential for permanganate, which was positive 1.51 volts, at least on the new chart. And oxidation of iron, we look up the reduction potential for iron 2, and we take the opposite sign. So I use positive 0.44 volts, and I get 0.195 volts with the new reduction potentials. Okay, electrochem number 2. We are going to take aluminum oxide and we are going to create aluminum from it. So do understand that when aluminum oxide is a compound, it's in a positive 3 oxidation state. So really what we're doing is, and I'm going to box it over here, is we're going from aluminum 3 plus down to aluminum. However, we have 2 atoms of aluminum, so we're doing 6 moles of electrons. So they gave me an amperage and they gave me a time, 1 hour, per 1 hour. So that's, if we go back to our little formulas, a coulomb of charge is an amp second. So they gave me the amps and they gave me the seconds. 1 hour is 3,600 seconds. So that gives me 5,400 coulombs. And then from there I can do the stoichiometry. 5,400 coulombs, and then Faraday's to get 1 mole of electron, and then 6 moles of electrons per 2 moles of aluminum ions. And then for every 2 moles of aluminum ions, you get 2 moles of aluminum. And then I looked up the mass of aluminum, and that gives me 0.503 grams of aluminum per 1 hour. For the third problem, we are going to completely remove all the silver ions from a 100 ml solution. So they're giving me the volume, and they're asking me to charge for, they're asking me to solve for the concentration of aluminum. So that's a molarity, moles divided by liters, and we already know that the liters, 100 milliliters is 0.1000 liters. So I just have to calculate the moles of silver ions. So I had to get up and close my office door. My kids are playing video games downstairs. Anyway, so I know when silver ions reduce to silver, you're going from a +1 charge, so 1 electron. They're giving me the amps. Well, they gave me milliamps, but I can convert that to amps. And they're giving me 15 minutes, which is the seconds. So 15 times 60 is 900 seconds. So that gives me 1.125 coulombs of charge. And once I know the coulombs, again, I can do the stoichiometry. I can use Faraday's to convert to moles of electrons, and then from moles of electrons to moles of silver. And then I just go back and I plug that back into molarity, moles of silver divided by 0.1 liters. For problem number 4, How many minutes to electroplate something? All right, so I'm thinking amp seconds here, and they give me 7.65 amps, and we're going to try to figure out how much time, so we can solve for the second. So a second is going to be an coulomb divided by amps. In any event, the only thing that's tricky about this problem that I don't like is, they're giving you the density. So, of course, if you had the volume, you could get the mass. And then they give you dimensions, 24 centimeters times 12 centimeters, and then a thickness of 0.020 millimeters. The thing is, you're not making a complete tray out of silver. What you're doing is you're just coating the surface of that tray. So they're not giving you the volume of the tray. What they're doing is they're giving you the thickness of the layer of silver that you're going to put on the tray. And the most common mistake in this is that most people do this problem and get 12.8 minutes. And that's because they fail to remember that the tray actually has two sides, a top and a bottom. So when you're calculating that volume, length times width times height, that volume is actually the volume of a coating for one side. And so when you get that volume, you get 0.576 cubic centimeters using the density. Then we can use the density to get the mass for that side at 6.07 grams of silver. But there's two sides, so we have to double it. And then we can convert grams to moles, and then moles to electrons, and then electrons to coulombs. So using Faraday. So we get 10,900 coulombs. And again, like I said, a coulomb's an amp second, so we can solve for seconds. And that comes out to be 23.7 minutes. Problem number 5. What was the issue with this one? Problem number 5 with this one is that they're asking you for certain information, but they're giving you the opposite information of what you need. E0 is just a reduction potential plus oxidation potential. And if you look at the cell notation for the cell, you're oxidizing iron 2 to iron 3 in the reaction. So the issue is that, we can use E0 equals reduction plus oxidation and solve for oxidation, but the question is actually asking you to go from iron 3 to iron 2, which is a reduction. So when we solve for oxidation, we get negative 0.77 volts, but they don't want the oxidation of iron 2, they want the reduction of iron 3, which is the opposite reaction. So we just change the sign, and we get 0.77 volts. Problem number 6. Remember I said that voltage is not stoichiometric, so the stoichiometry comes in this particular problem or this formula where they're saying, all right, we want KSP. So we know we have to use the natural log of K is NFE over RT. But the problem is that KSP is the dissolving of silver bromide into its ions, but the information they're giving us isn't KSP. They're giving us silver bromide breaking up into silver metal, which is a reduction of silver. So they're giving us the reduction of silver in the first equation, and then they are giving us the ionization. If we flip that second equation, it gives us the ionization of silver metal to silver ions. So this is a little bit of Hess's law. If I add the two together, then I can calculate E0 by adding E1 plus E2. And I get negative 0.728 volts from that when I looked up, from the potentials they gave me in the problem. Now I can substitute into my natural log of K. And when I do that, I get KSP as e to the negative 28.4 or 4.6 times 10 to the minus 13. The 7th question. All right, what was the issue with this one? They want delta G. And we know delta G is equal to negative NF E0. And the equation that they gave us is fine, and I diagrammed it up there. We have the oxidation of silver going from 0 to +1. We have the reduction of fluorine molecules becoming fluoride. But they don't give us the information that we need, so we have to manipulate that information. And the information they give us is for instance, in that first reduction potential is for 1 mole of silver, and then you're tempted to take the number and double it, the 0.799 volts, and double it. But you can't. That's for delta H, but you don't do it for E0. E0 is not stoichiometric. So we're going to use the value they gave us, but we're going to flip that first reduction potential because we need the oxidation of silver, not the reduction of silver. So they did give us the reduction of fluorine, which was good, and I just added that to the flipped reduction of silver ions. And that gave me a net of 2.071 volts. And then I can substitute in, now the number of moles of electrons, that's where the stoichiometry part comes in. That normally we would do silver becomes silver plus 1 electron, but in our reaction, there's 2 moles of silver. So that's where the 2 comes in, right in here. So 2 moles. And so when I substituted in, I got delta G at 4 times 10 to the minus, pardon me, 4 times 10 to the minus 2 kilojoules. Now the last question, like this one. Standard electropotential for the following reaction. So they give us E naught. E naught is 0.588 volts. What's the potential when the pH is 8? So if I'm looking at the reaction, I'm producing 4 moles of OH minus. So fine. One, I have to recognize that the pH gives me a pOH of 6, and that gives me an OH minus concentration of 1 times 10 to the minus 6. And the word potential means E. Standard potential means E naught. The word potential means E, or the measured voltage. So I can use the equation E equals E naught minus RT over NF times natural log of Q. So Q is going to be products over reactants, so hydroxide raised to the 4th over permanganate. And then I just substitute in those values and I get Q at 1 times 10 to the minus 24. And then I substitute into my equation and I get a voltage of 1.061 volts. All right. Enhanced with sound this time. So thank you very much for listening.